So, Krista, do you want to share your slides?
Yeah.
So our second speaker of the day is Crystal Meriwether Keller, who's going to talk about a statistic given a Q analog for a formula for the number of k-Naples parking functions.
So this was joint work with Laura, Pamela Harris, Zakiah Jones, Andres Arvindas Melendez, Andres Ramos Rodriguez, and Eunice Sicarto through the UMass Math RU and the Advancing Inquiry and Inclusion in Mathematics undergraduate program this summer. I had to include my middle name just so I looked like a significant part of the list of collaborators here. So before we can talk about k-Naples parking functions, we should talk about regular parking functions. And these are the ones that we're going to call zero Naples. These were originally defined in 1966 in a paper by Cohnheim and Weiss on computer storage as solutions to computer hash map collision problems. So we'll look at my more mathematical definition here. They had a fun story about cars, about people's personal lives, but I'm going to strip that out. So imagine that there's n cars and they travel down a street. This is supposed to be a car down here, if you can see my mouse, with n parking spots. So it was P in the original paper, but Pn. I didn't want you to think it was prime. So each car has a spot it really likes, one of these n spots, which we'll call Pi, corresponding to car Ci, which I guess you could just call I. So each car drives down this one-way street to the parking spot it likes, and if the spot is empty, it parks there. Otherwise, it keeps going down because it's a one-way street and parks in the next available spot if there is one. So if the cars are able to park successfully, the list of parking preferences, the spots the cars wanted to park in, is called a parking function of length n. They have some examples. So for example, a permutation is a parking function. If each car wants to park in a different spot, as each car comes in, its spot will be open because no other car ever wanted to park there, and every car before it has been able to park successfully. So each car, the ith car, will park in the pi ith parking spot for a permutation pi. The cars park, so it's a parking function. Another nice example is the situation where all the cars want to park in the first spot. The first car will come in and it will successfully park in the first spot because no one's parked there yet. Then the second car will come in, it will try to park in the first spot but see that it's full, continue down to the second spot and be able to park there. Similarly, the third car will try to park in the first spot, see that it's full, drive to the second spot, see that it's taken, drive to the third spot, and park there. So each car I will park in the ith spot. But not every combination of numbers like this is a parking function. For instance, if all the cars want to park in the last spot, so there's n copies of n, then only the first car will park. Or I should say this is a parking function if n equals 1. If there's only one car and it wants to park in the only spot, then it will park. But as soon as there's two cars, the first car will park in the second spot. The second car will skip the first spot to check the second spot, see that it's full, and have to drive off the road because it can only drive one way.
Ask a question.
Yeah.
Yeah, so you said that all of the cars, they're just like trying to start from the first place. So is that the function that you're saying? Isn't there like a, like you talked about hash table, hash function? So just, I was thinking whether each of the cars are supposed to have like a specific spot, like hashed to a specific spot. And
Right.
then if there is space not available, then it goes to the next. But what you said is it always starts from the first. So what's significant about it?
The cars, when I said they were all starting from the first spot, I was talking about the parking preference 11111111. So that basically the idea there was that all the cars were being hashed to the first spot. But that's not the only hash. Okay. So the function is, it's a function from the set of cars to the parking spots. And so if the cars collide, if both of them want the same spot, then you can try to resolve it using this rule, where if there's a collision, the second car tries to park in the next available spot.
But you start with the cars having the same preference is what?
So each car has a preference. They don't have to be the same. That was an
Okay,
example
I
of a
see.
park.
So this is an
So
example. Okay.
Right. So again, a permutation won't be like that. If the first car wants the second spot, the second car wants the first spot,
Cool.
then the first car will come in and it'll check the second spot immediately and park there. I think the language makes this confusing because we're talking about cars driving down the street. When they drive down the street, they have to start from the beginning. But really, there's
Yes.
nothing. The
Yes.
driving is not part of the mathematics of it in any way. It's just a story. So there's another example of something that fails to be a parking function. It's a special case of what I was just talking about. And similar, maybe this clears things up. 232 won't be a parking function. So if the first car parks in the second spot, the second car parks in the third spot. So at this point, the second and third spots are full and the first spot is empty. Then if the third car wants to park in the second spot, it'll see that that was full because it was already taken by the first car. And so it'll continue down to the third spot and see that that's full because it was taken by the second car. And so it will fail to park. So this would be a parking function. Now, these were generalized last year to k-Naples parking functions, which were defined by Baumgardner in a paper from Florida Gulf Coast University and studied by the AIM-UP program last year. So the idea here is to expand the list of parking preferences that become parking functions, or now k-Naples parking functions, by changing this parking rule so that when a car finds its spot is taken, rather than immediately moving forward, it checks k spots behind it. So it tries to, if it's one Naples, it basically tries to parallel park back into the spot behind it. Or if it's two Naples, it tries the spot behind it, then two spots behind it, and so on. And so now you can see why we called the regular parking functions 0 Naples, because the cars didn't try to back up at all. They immediately moved forward. So if you want to say this explicitly, suppose n cars travel down a street with n parking spots. Each car wants to park in a spot. If the spot is empty, the car parks there. Otherwise, it tries to parallel park one spot behind, then the next spot behind, and so on, k times before moving forward, just as before. If the cars park successfully, it's called a k-Naples parking function of length n.
Where does the name come from? Is it how they park in Naples?
I've been so familiar with this that I forgot that it's a really weird name. Yes, it's based on what the author thought people parked like in Naples. However, I've heard from different people both that this is about Naples, Florida, which makes sense because the person is from Florida.
Yeah, otherwise they
And-
would have called it Napoli, right?
Yeah, so I believe it's about Naples, Florida, not Italy. If anyone is ever in Naples, I suggest you tell me if people. So the original Naples, when they defined it, it was not k-Naples; it was one Naples. That was the one. So they're saying that people in Naples parallel park a lot. If you're there, you can check. I'm not sure. Anyway, so we have examples of these. Any parking function will be k-Naples because the rule only ever moves cars backwards. That says it's unstable. I hope so. 3133 is from Naples. So the idea is the first car parks in the third spot. The second car sees the third parks in the first spot. In fact, I don't know why I haven't been drawing this out. I have the ability to annotate. I should have done that. It might have made this clearer. So we have 4 spots. 1, 2, 3, 4. The first car wants to park in the third spot, so it does that. The second car wants to park in the first spot, so it does that. The third car wants to park in the third spot, but it sees that it's full. But now it's able to parallel park one back, and it parks there. And then the fourth car tries to park in the same spot, sees that's full, sees it can't parallel park, and so it moves forward and parks in the last spot. You might notice this wouldn't have been a regular parking function, because if car 3 couldn't have parallel parked, it would have had to move forward and park here. And then the fourth car would not be able to park here or here, and so it would have nowhere to park because it couldn't move backwards. There we go. And so every parking preference is k-Naples for some k, because if you take k equal to the number of spots minus 1, then, for instance, then every car will be able to check every spot. Of course, once you get to the last spot, there's no spots behind it. So, for instance, the last car will be able to check all the spots. There's n car and n spots, and they check all the spots, so they'll all be able to park. The question is going to be how many parking functions of k-Naples parking functions are there? And so a recursion for this was given last year, but we found a enumeration which is not recursive.
Krista, we
So
have
the
some questions in the chat for,
Mhm.
so like, if let's say that you're trying to park in the second spot and you're 4 Naples, so then you would check the first spot and then you would not like cyclically check the last spots. No. So
Right.
you
I
would
guess
just,
I tried to say that when I was talking about this. I didn't make it clear though. Once you get to the end, so you park up to k spots back, as many as there are. So no more than the last spot. Is that the only question? Let me look at it. So
Yes.
k could be bigger, right? So that was just the same question. One.
The point is that it wouldn't matter, right? Because if you reach the first position, then after that you're going to check all of them anyway. So if there is one open, you're going to sit there. Is that the idea?
For the k equals n minus 1. Is that what you mean?
For k being larger than your preference.
I mean, if you did it cyclically, right, you would get a different parking in the end, right? So it
Yeah.
might actually change it.
So this idea of cyclic parking is actually what's used to prove the easy way to prove the number of 0 Naples parking functions is n plus 1 to the n minus 1, where n is the number of parking spots. And you might notice if you take n, well, equal to n plus 1, then you get n to the n minus 2 here. And yeah, that's the number of a lot of other things. For instance, labeled trees on n plus 1 vertices. And there are bijections known for stuff like that. But it's not clear how to extend this to bigger numbers. We don't have a formula like this. So that would be nice. So instead, we count the parking functions by by taking the sum and splitting it into all the different orders the cars could park in. And then we're able to just analyze what's going on by cases. So for example, if we were talking about the parking lot, if we want to count the number of parking functions, 2 Naples parking functions that end up like this: car 5, car 1, car 4, car 2, car 3, then I guess my text is going to show up over this, but I think I can move it somehow. Then when the 4th car comes in, the 1st, 2nd, and 3rd cars have already shown up. So the 1st, 2nd, 3rd cars are already in their spots, which means car 4, well, it can't try to park in the first spot or it'll end up in the wrong spot. It's supposed to be in the third. If it tries to go to the second, then the Naples backing up rule will put it in the first. So that doesn't work either. But it can, of course, try to park in the spot it actually wants, or the spot after that, because then it'll back up into it, or the spot after that. And so you can use this method to determine the number of possible parking preferences for each car, sort of recursively. So the first car had to have picked the second spot because it gets to park wherever it wants and it has to end up with the first spot, and so on. You continue like that. Now, what complicates this a little bit is that we actually have two cases to worry about. So if when a car comes in, all the parking spots to the left of it have already been taken, it can choose any of those. And then it'll just be pushed down the line because it doesn't move cyclically. But if it's not all of them, as in case 2, then only some of the spots will work. So for instance, if the car tried to park here, or if that was its preference, then it would end up getting pushed back to here. So it can't choose 2 in case 2, but it could choose 2 in case 1. So basically, we're going to count the preferences that are smaller than it, the cars that have the cars that are smaller than it to the left, the cars that came in before it to the left, and depending on whether it's all the way to the end or not all the way to the end, we'll have a little bit of a different count. And so we have a really painfully large way to do that that isn't really complicated. It's just a lot of symbols. So the left is the subsequence to the left that has already shown up, and right is the subsequence to the right that has already shown up, as long as it's not more than k, because if it's to the right, it has to back up, and it can only back up at most k. And so these conditions just correspond to case 1 and case 2 before. Either the number to the left that have already shown up is all the numbers to the left, or it's less than the numbers. And this just codifies what we were talking about. So for instance, the length of the third spot was 4 in our example. In this sequence, 5, 1, 4, 2, 3 is 3, because there's no spots to the left that work. If you want to be careful here, you know that the sequence left k is not all of them. So we're in the second case. And then the maximum of 1, which is the length here, minus 2 is negative 1, 0. So the maximum is 0. And then the right, well, the right is defined to include the thing itself. So 1, 2, 3. And so there's 3 options for that spot.
So sorry, why is right k 3 in that case?
So there's 2 spots to the right, and then either left or right has to include the spot itself, because the spot itself is also a preference. Does that explain it? So you can park in either of these 2 spots, because if you do, the cars 2 and 3 have already parked there, and the 2 Naples rule will cause the fourth car to park in the right spot by bumping it back. But there's also the case where the car can just choose, I want to park in the third spot. Maybe it's a confusing name and it should have been left plus right plus 1 to account for that, but we included. So you can think the left is strictly less than, the right is less than or equal to. So 4, 2, 3 are all less than or equal to 4. 1 is the only thing less than 4. But then 1 minus 2 is negative 1, which is less than 0. So I think that's the most confusing formula here, but it's not really complicated. It's just technical. Are there any other questions about that? Okay. So then we can introduce even more symbols to look fancy and say that the number of parking functions is the sum over all of the possible parking preferences, basically what comes out to all the ways the cars could have parked of these LK symbols, of the products of these LK symbols. So there's 3 options for 4, and there's going to end up being 1 option for every other car. So, or sorry, five. So 5 will have some other options. There'll be 3 options for 5. And so the total number of parking functions that map to 51423 will be 9. I went through that really quick, but is it straightforward enough? Okay. In other words, we just gave a way to count the number of parking functions. Now these parking functions are able to be thought of as, and this is just for the 0 Naples parking functions, as labeled Dick paths, which are these paths in the lattice, where the fact that this is 2, 1, 2 corresponds to the fact that there's one thing that's in the first column and 2 things in the second column, because there's 1, 1 and 2 2s. And so then you can label it with the location that those numbers appear to give a bijection. So the 1 occurs in the second spot. So there's 2 there, and the 2s occur in the first and third spots. Now there's something called the area statistic on this, on these objects, which is the number of full boxes. So in this case, the area of 212 is exactly 1, because there's only 1 full box. That's so that the corners here don't count. And you can, there's a formula if you want.
Christo,
Yeah.
Theo is asking, before you move to the area statistics, what does the decomposition of PF and K imply for the usual K equals 0 case?
So it implies that when you set this K equal to 0, so these K's equal to 0, so K equal to 0 here also, then you get that this is a way to calculate the number n plus 1 to the n minus 1.
No, I understand. I mean, is the product of L sub k of that some nice statistic on the permutation sigma?
So in the K equals 0 case, right K will always be 1. And then I'm not sure if there's a statistic named like this, if that's what you mean, that's studied.
It's just it would be a really cool thing, right? Because you're decomposing the trees as not exactly a statistic, but somehow this blow up of its permutation. So you can interpret the product via something that relates to the permutation sigma, that would be really cool.
So maybe something like that is actually what we're about to do with the area statistic, but I don't know about thinking about this as a statistic on the permutations, although that makes a lot of sense. We didn't think about it that way. So we have this area statistic, and we're going to have the Q analogs of numbers defined this way. So the Q analog is a polynomial with n terms corresponding to the number n, which when you take the limit as q goes to 1 of n, you get n, while stealing more information about whatever you're talking about. So in this case, we actually have that the products of the Q analogs when k equals to 0 is the sum over the parking functions of q to the area. So that's what I meant when I said something kind of like that is what we were going to come out with in a second. So the idea is that parking functions only shift, like there's a maximum Dick path that goes along the diagonal. And as you move those down, that corresponds to choosing things less than L. I guess I'm taking a lot of time here, but I'll try to talk about this at least. Maybe have to skim over the K stuff, but the left-hand side, so this function with the Q analog of the L's is a generating function for pairs of objects, a permutation set by the sum, and a bunch of numbers u1, u2 up through un that are less than L naught. So of I. So that because the Q analog is going to be 1 plus q plus q squared plus q cubed. So basically you're choosing a power of q less than this number for each index and multiplying them together. And so you'll be able to take those ui's and send them to sigma I minus ui, where sigma you can think of as the parking order, and that will give you a parking function. And you know it'll give you a parking function because a permutation is a parking function. And if you reduce the terms in a parking function, you still get a parking function. And you'll keep the permutation itself, for instance, because 0 is always less than any L, less than or equal to any L naught. Or less than any L naught. And then you can show everything that it's a bijection. Not very difficultly. And so then we were able to generalize this to the k-Naples case by defining an area statistic in quotes, which I'm going to gloss over because I think this is the end of my talk. But it doesn't correspond to area in the sense that the other area statistic did, because there is no bijection from general k-Naples parting functions to labeled dict paths, only 0 Naples. But it's area in the sense that it's shoehorned in to make this bijection work for the k-Naples case. And so I gave an example of that, and it just means stick k's everywhere in the theorem. And then there's the bijection. And there's other things we might do with this. So the way we did it was very forced in order to make the statistic work in the k case, but there's all different generalizations of parking functions. So there's similar formulas for this, and do they correspond to some other statistics? Is this statistic equivalent to any other statistics? Does it have the same distribution as some statistics that could be defined? And is there a way to generate this recursively? I have no idea. I mean, I'm sure, I imagine there is one, but I don't have it. And so that's all I had to say. Are there any questions about any of that? It got really fast towards the end because I ran out of time, but.
No, it was good. There were also questions during the talk, so. Any other question?
Yeah, so if you, so I guess you mentioned that when k equals n minus 1, you get every function.
Mm-hmm.
Or so is it possible to, if I give a function, is it possible to calculate like what k it like yeah, where it fits on this pkn, like which k, for what k is it a k-Naples parking function, or maybe or an average maybe?
So you can
also
certainly try them.
Mhm.
You know, start with 0, 1, 2, 3 until you get to it, and to the smallest. It turns out to be really hard, pretty hard anyway. We only worked on it for a little bit, so I can't say it's really hard to talk about like when rearrangements of k-Naples parting functions will be parting functions, or what k they'll be in. That was a question that we considered. But unlike with regular parking functions, if you take any rearrangement, it's still 0 Naples. But that isn't always the case for other ones. I can tell you that there's some tricks, like the increasing rearrangement of any k-Naples will also be k-Naples and stuff like that. But and that I guess makes sense because it's sort of like the best case scenario of later cars are moved further to the right.
Okay, I see.
But I don't know a way to quickly check which k it would be. Like if the k ended up being 57 or something, you'd have to, the quickest thing I can think of is to go through all 57. But that would be an interesting question to look into.
So related to what you said, the fact that you can rearrange the parking functions in the case equal to 0 case is very interesting, because it means that the symmetric group is acting on them, and then the orbits are enumerated by Catalan numbers and Narayana numbers if you refine. Since you don't have that property here, do you maybe at least even by accident have some nice enumeration for the increasing ones? Like if you only count the increasing k-Naples functions, do you get anything interesting there?
Yeah, so the increasing, or you could say decreasing equivalently, k-Naples, you can make a bijection with the Dick paths again. It won't be a Dick path exactly, but it'll be a lattice path that doesn't go more than k past the line. So in other words, you can think that the line is moved over k. I guess I should try to draw this instead of clicking with my mouse. So like a k equals 1 parking function might be something like this. That's not drawn right.
That is true.
Something like this. There's the way to draw a line and zoom. Yeah, there we go. So where the line is here instead. And it looks like this. That was a result from the first paper on this. And there's a way to count those. There's a difference of 2 binomials, actually, which I guess specializes to the n plus 1 to the n minus 1 again. So you can count the increasing rearrangements, yeah, and the same thing, the decreasing rearrangements. But what's difficult is the arbitrary rearrangements.
Yeah, we weren't even like, our first approach was thinking if there was only one bump coming between the 0 diagonal and the other one, and
Yeah,
not
so
even
only one spot over.
are very easy.
Unless you know something about where the cars actually park, right?
Mhm.
But even that's not clear.
But that's probably our project for next summer. Like it's hard to work with undergrads when it's the semester, but it's probably what we're gonna be doing next summer.
And since this was through the AIM Up program, we actually only spent a single month on actually thinking about this. So it might not be as hard as we think. Any other questions?